Hello class, this is Brian and I'm here to give you a short video going over some of the major concepts of the first week of MAT-240 Applied Statistics. First of all, a little overview of what I see as the role of statistics and what we're chiefly concerned with. We're looking at trying to learn something about a large population, and the population could be people, it could be organisms, it could be cars, it could be any large group of individuals that we can't look at in its entirety, so we take a sample. And from that small sample, we do some sort of calculations and come up with some numbers, and these numbers are what we call statistics. So a statistic is any number that is somehow derived from a sample of data. Statistics are going to be used for what we call inference, which is trying to say something about the population, inferring something about the population. And the two chief tasks are estimation, estimating parameters of the population, parameters being some aspect of the population that we're interested in, like the average height of a poodle in Ecuador or something like that. Parameters are what we want to know about, but we can only estimate. And then there's decision making, which is to something like has the proportion of people who are buying iPhones increased in 2017 or not? So making a decision yes or no, or choosing between different alternatives. Those estimation and decision making are the two tasks that we use statistics for chiefly. Statistics come in two different types. Descriptive statistics are describe the sample data. So we're going to be looking at a number of descriptive statistics: the sample mean, the sample standard deviation, the sample size, things like that. Inferential statistics are used in our inference. So statistics that are used to infer something about the population itself. Okay, and now to begin the course, we're looking at just an overview of some ways of visualizing data, and I want to touch on some of the most important things. And the first is, what's the difference between a bar chart and a histogram? And the key differences are shown here. A bar chart has a bar giving a height for any number of categories, and these categories could be displayed horizontally in any order. There's no real reason to have them in one order or another. You might use alphabetical order or color order or height order or something like that. Also, we put gaps between the bars in a bar chart. On the other hand, a histogram, each of those bars represents a numerical range. And so the height of the bar is how many times some number has showed up in our data that falls within that range. And so we don't put gaps on a histogram because we want to see this shape. And also, of course, the number ranges can't be ordered in any way we want. We have to put them in increasing order. So those are the main difference between a bar chart and histogram. We'll chiefly be using histograms in this course, not bar charts. We'll be looking a little bit at time series, very, very little bit, but the main idea is similar to a histogram. You can't order things in any way you want. You have to have increasing order going horizontally. You have a data point for periodic observations of data, and you just kind of plot the points and connect them with a line. And this is how we can see if there is some general trend or something like that. We're not going to really be getting in deep into time series, only a little bit in Module 1, very briefly. The other thing I want to mention about data is whether we're looking at the frequency of data or the relative frequency. And here I'm showing two histograms, and they look almost identical. The one difference is the axis on the left. You can see on the first histogram, we're charting the frequency of various observations of data. So whether, like in this case, it looks like there was one individual who has a height between 45 and 47 and a half. That's halfway between 45 and 50. One individual, where and so the bars go up in unit one in frequency blocks. In the second, it's relative frequency, so it's all in proportions of the whole. So if you look at the height of each of these bars, this is what proportion of one is made up of by that bar. So frequency histograms and relative frequency histograms should look the same in shape. It's only a matter of scaling on the y-axis or the vertical axis. Histograms, one aspect of their shape that we're concerned about is skew. A skew is a kind of the shape being pulled in one direction. The first histogram is, I would say, more or less symmetric. It's certainly not, it's not perfectly symmetric, but it does, I would say it's pretty symmetric. But on the second histogram, there's definitely this asymmetry, and you see this, what we call a tail trailing off to the left, and that tail is where we have the skew. So we would call that a left skewed distribution, or left skewed histogram. That's what skew is. There's actually numerical measures of skew as well. We're not really going to get into it, but you can easily, with software, calculate the skew in a data set. One way of visualizing data is with a box plot. And here you imagine you have a set of numbers, a whole bunch of numbers coming from some sample data. So it's a whole set of numbers. If you were to order them from lowest to highest and just plot each one along a number line, the box plot is a way of kind of representing that and simplifying it. So what we do for all the data that isn't a so-called outlier, we kind of break it up into quarters. So we call these quartiles. The first quartile is the point at which you have the first 25% of your data. And then the second one, quartile 2, also known as the median, is the 50th percentile. That's half of the data is below that point, half of the data is above that point. Then you have the 75th percentile, also known as the third quartile. And then you may go up so the maximum data value is going to be represented, in this case, by a dot. The dot that's furthest to the right is the maximum data value. But you have, in a box plot, these little, what we call whiskers that show the fence. It's also whiskers or a fence breaking, kind of separating what are outlier data from the non-outlier data. And that's actually calculated in a very specific way. I don't want you to be too concerned with it, but this distance from the first quartile to the third quartile, that's called an interquartile range. It's just a length. So in this case, it looks like it's about 22 or 23. The interquartile range is about a length of 23. So what you do is you take 1.5 or 1.5 times 23 and go that far to the right of the third quartile and that far to the left of the first quartile. That is going to be the cutoff for outliers. So I've approximated that with a dotted line, and so those two dots are data points, which are outlier data points. So you can always check whether or not there's outliers in a data set by plotting a box plot and selecting an option to show outliers as dots. So box plots are handy. They could give you a sense of the data. In this case, because you have the median is not in the center of that box, and you can see that the rectangle on the right hand side is longer, and then you even have the data trailing off to those two outliers. That tells you that there's a right skew in this data set. So there's a number of descriptive statistics that we use to describe the center of a set of data. First, the mean is what we're going to spend most of the time using. The mean or average, if we ever say average, we probably are referring to the mean. It's in physical terms, it's a center of mass, and it's what we're most familiar with. To calculate the mean of a set of data, you would add up all the numbers and you divide by how many numbers there are, sometimes called n. So if you have the total already, you could get the mean by just dividing by how many there were. But some things to note: the mean is affected by extremely large or extremely small values. They have a big impact on the mean. And the data must be numerical. Of course, in this course, we're going to be using numerical data most or pretty much all of the time, but sometimes you don't have numerical data. You have, say, categorical data. You're asking people what their favorite color is, and so you can't have an average favorite color in this sense. It doesn't mean anything to say their average color is. You can't average, black, blue, and green and have a meaningful average. Because it's affected by extreme values, the mean is going to be, we can say, biased by a skew in the data set. So sometimes we'll say if the data is very skewed, then it might not be appropriate to use the mean as the center of the data. In that case, we would use the median. The median, 50th percentile, it's the halfway point in the data, so it's a number that splits the lower half of the data from the upper half of the data. So if you order your numbers from lowest to highest and just count it so that you have half of the numbers, you split it after half the numbers, that'll be the median. I'm not going to be concerned with how you calculate formulas or that kind of thing, because we're going to use software to calculate all these numbers. I don't want you to have to use formulas for any of this stuff. So the median, it's not affected by extreme values. And so if the data is skewed, the median is going to be more appropriate. And the data doesn't necessarily have to be numerical, but it has to be orderable. So it's a little bit more flexible. The mode is the most flexible, but also, in my mind, least useful. Concept of center. The mode is just the most common value. So in a histogram, the mode would be the peak of the histogram, whereas the highest point. And some data sets have multiple modes. We call that bimodal or trimodal or multimodal. But if it's unimodal, which means one mode, that's just one peak or one crest of a mountain, so sort of. Anyway, the mean and the median are what we're going to use most of the time, and the mean is the most important for this course. To describe also spread. So spread is a way of talking about how far does the data spread away from the mean. So a very simple descriptive statistic would be the range, which is just it's a length between the minimum and the maximum values in the data set. It is just the maximum value minus the minimum value. The interquartile range I mentioned before, it's the range between quartile 1 and quartile 3. So you take the difference of those two numbers. Those both give you a sense of the spread, but they only incorporate a couple of the numbers from the data set. What we're mostly going to be using is variance and standard deviation. The variance is a sort of average of the squared deviations from the mean. So for each number in our data set, you calculate what is the difference between that number and the mean of the data set. And that difference, you square it, okay? And then you add up all those squared differences, and then you divide by, you don't divide by n, which is the number of numbers in your data set, but n minus 1. Well, anyway, we don't have to do that by hand. We have calculators and we have software that'll do that for us, but that's just what variance is. Important to know, it's an average of squared numbers, which means the units are going to be squared too, and so it's not interpretable in a meaningful way. The standard deviation, on the other hand, it's the square root of variance, so it is interpretable. The units are back to the units of the data set. If we were measuring the heights of poodles in Ecuador, the variance would be in squared feet, which doesn't have a meaning, but the standard deviation would be back into feet. Well, we probably use centimeters or something like that. And then a kind of interpretation for standard deviation, which is a good rule of thumb, is that if you take the mean of the data set, within about 2 standard deviations, we'll see about 95% of the data, more or less. This is a rule of thumb, so it's really most appropriate if our data is normally distributed. We'll talk about that next module. But anyway, it's a good here, like a simple rule of thumb that you can use. Okay, so next we want to talk about the concept of a random variable. And really you want to think about it's some unknown number, and imagine some number. Every time you look at it, the value is different. Okay, so it takes different values with certain probability. So there's some probability that the number is going to come up as a 3, some probability it's going to come up as a 20, whatever. And if we know something about those probabilities, then we can describe this random variable in some way. And really the way you want to think about it is if you have a population, so a huge population of individuals, and you start sampling individual people or individual members of this population, every sample is like observing a random variable. So you can think of it like some die that every time you roll it, you get another number. Well, it's like every time you randomly take a person from the population, you're seeing another value. So that's the sense in which we want to think about random variables, because in statistics, we're talking about sampling from a population. Discrete random variables are random variables that describe something that's counted. So the number of children in a household, the number of jobs that someone has had during their life, the number of grains of sand on some various beach. If you take a random beach, the number of grains of sand, although it can be astronomically high, it's still just, a countable number. Continuous random variables are measured, and they can be measured with any level of precision that we have, that we feel like using. So the heights, length, duration, weight, volume, these are aspects that are measured rather than counted, and so those would be continuous rather than discrete. So for discrete random variables, we can represent the probability in a table, and so you can list each of the possible values or outcomes of the random variable and the associated probability. And the important thing to remember about probabilities, it's a way of talking about the relative likelihood of one outcome versus another. And so a probability is a number between 0 and 1. We'll usually represent them as decimals, so 0.22, for example. You could represent it as a percentage, like 22%, but it's never going to be negative, and it's never going to be greater than 1 or 100%. And now when we have a probability table, we have to be sure that every outcome has an associated probability with it. Even if a probability is 0, that's okay. It just means that outcome can never happen. And the other thing is that the probabilities add up exactly to 1. Otherwise, you would say it's not a valid probability table. So if one of these probabilities was left out, it was blank, we would know how to get the missing probability. We would just add up the other probabilities and subtract that total from 1. That must be the missing probability. And the last concept that's important is the concept of an expected value. It is actually very much related to the mean, but in a I'll say a probabilistic sense or a theoretical sense. So an expected value of some probability distribution like this would be a theoretical long-term average. What I mean by that is, if we were to imagine the four-sided die that is displayed here, which comes up as 0, 1, 2, or 3 with those associated probabilities. If you were to roll it again and again and again and again and again, if we were to do that forever and then take an average value, well, that would be the expected value, the average of all of those rolls. And it's relatively easy to calculate as far as formulas go. It would be, you take each outcome, multiply it by the probability, and you do that for all of the lines in the table, and you add up all of those products. But you can also use software to do that, and I will show you how to do that in another video. And so, yeah, the expected value is also the mean of a probability distribution. It is the center of gravity or the center of mass in a probability distribution. It would be like a balancing point if you had this represented in a physical sense on a scale.